We are going to continue working on solving quadratic equations. In this particular video, we're going to look at the idea of taking square roots. What we have done in the past is factoring. And when you had something like this that didn't have a b term in the middle, we would put in that 0x and we would do ABC. But if I try to do that on this one, a is 1, c is -5, 1 times -5 is -5. I cannot think of two integers that multiply together to be -5 and add together to be 0. So I need a different process on this one. This one is not going to factor with integers like what we've done before, so we need something different. So when we do the square root idea, the goal is to isolate the squared thing and then take the square root of both sides, because squared and square root are opposite. So let's add 5 to both sides, working to get that x squared by itself. And now I'm going to take the square root of both sides. Okay, now think for a second. When I square something, whether that something is positive or whether that something is negative, I end up with the same answer. So when I unsquare it, when I look at the square root, I have to allow for the fact that that number I squared might have been positive and it might have been negative. I have to put two solutions. And that makes sense because my highest exponent is 2. Fundamental theorem of algebra tells me how many solutions I ought to have. So when my highest exponent is 2, I ought to have 2 solutions. All right, on the left-hand side, squared and square root are inverses. So I'm going to end up just with x. On the right-hand side, plus or minus the square root of 5. I would try to simplify this. In this case, 5 is prime, so there's nothing to simplify. If you look at a graph to see what we have found, this pink parabola right here is x squared minus 5, and you can see that it crosses the x-axis twice. This value that's a little bit more than 2, this is the positive square root of 5, and this value that's a little bit less than -2, that's the negative square root of 5. So when I'm solving a quadratic, the solutions that I get when it's set equal to 0, the solutions that I get are the x-intercepts. So some vocabulary you need to be familiar with. This plus and minus 5, that's the solution of this quadratic. If I look at y equals x squared minus 5, it has two roots, and those roots are positive 5 and negative 5. And if I look at the graph of that quadratic, it has two x-intercepts, positive 5 and negative 5. So x-intercepts, roots, and solutions, they all end up to be this, and those are some words you need to be familiar with. You might see any of those words on a standardized test or perhaps in your college algebra classes. All right, let's look at this one, x squared plus 18. Well, I'm in the same situation. I do not have an x term right here. If I try to do a 0x, because 18 is not a perfect square number, it won't factor in the integers. So let's use our square root idea to solve this one. I'll subtract 18 from both sides to isolate the square root. Squared and square root are opposites. So I'll take the square root of both sides. Don't forget your plus and minus, right? Because when you take the square root, you need to allow for both of those possibilities. Now, 18 is not a prime number. 18 I can do a factor tree on. So let's do that really quickly. 9 and 2. 9 can factor further into 3 and 3. And then I'm going to cross out all my composites so they don't get in my way. And now I'm ready to do some circles. Because it's a square root, how many numbers should go in the circles? Well, I should have 2 numbers in the circle. So I've done this. And also remember that I had a negative right there inside of my square root. So when I get ready to write my solution, square root and square root on the left-hand side, I'm going to get x. I'm going to bring down that plus and minus because I need to allow for both possibilities. All right, looking at my factor tree right here, the number that will come outside is 3. And then when I have a negative inside the square root, what does that tell me? That tells me my answer is imaginary. So I have a 3i because of the negative. And then left inside the square root, the only thing I have left over here on my factor tree that's not circled or crossed out is 2. So that is the solution to this quadratic. This x squared plus 18 has 2 imaginary roots, 3i squared root of 2 and negative 3i squared root of 2. And if we look at the graph, we can see that this parabola, x squared plus 18, never crosses the x-axis. It does not have any x-intercepts because the roots that I got are imaginary, And I cannot put imaginary roots on a real graph. I would have to put imaginary roots on an imaginary graph, which we're not going to learn how to do this year. We're going to focus just on the real graphs, and so this means I don't have any x-intercepts. Okay, let's look at one like this one. So instead of having this one equal to 0, this one is equal to 17. But unlike the quadratics that I did before where I wanted it to be equal to 0, my goal when there's no x term right here is to isolate the x squared. I want to get this one by itself. So instead of subtracting 17, I'm going to subtract 8 from both sides. X squared equals 9. 17 minus 8 is 9. Take the square root of both sides. Don't forget to write your plus and minus, two solutions. So I get x equals, bring down my plus and minus, and the square root of 9, that's one we might have memorized. 3 times 3 is 9. So x equals plus and minus 3. Okay, graphically, let's look at what we have here. The x squared plus 8 is this pink parabola. Y equals 17 is this blue horizontal line, and you can see that they intersect each other twice. So my answer is this positive 3 and this negative 3. So you might be wondering why I'm only focusing on the x value of the intersection. All right, well, look at the way this was given to us originally. This is not a system of equations. This is just an equation, and it just has one variable. It just has x. So when I write the answer, I only want to write the x value. I don't need a point because I didn't have a system with x's and y's to start with. I only had this one variable. So my answer is going to only be the x part, positive 3 and negative 3. All right, let's try this one. It's written a little bit differently, but the process is the same. Trying to isolate that x squared. So I'm going to add 8 to both sides, get my squared term by itself. Negative 17 plus 8, negative 9. Square root of both sides. This time I remembered to give myself enough space to put that plus and minus in there. On the left-hand side, squared and square root are inverses, so I get x equals plus and minus. Okay, now y'all look, I've got a negative right there. What does that mean for my solution? Well, it means it's going to be imaginary. So the square root of 9 would be 3. The square root of negative 9 is 3i because it's going to end up being imaginary because I have that negative inside of there. All right, graphically, let's see what we have here. So here's my pink parabola, x squared minus 8. Here's my horizontal line, y equals negative 17. And you can see that they never cross, right? So I got imaginary solutions to my original equation because there is no intersection point on my real graph. So imaginary solutions, no intersection point. Okay, let's try this one. This one looks a little bit different because it's not just x that's squared, it's x minus 4. But this is still all squared together. My goal is to isolate the thing that is squared. And in this case, this whole thing is squared. So I'm going to take the square root of both sides, remembering to put my plus and minus. So here on the left-hand side, squared and square root are inverses. So what I'm left with is x minus 4. Square root of 25 is 5, but I got to remember that plus and minus. I'm going to add 4 to both sides. Okay, so this is a little bit tricky because 5 and 4 are like terms. They're both integers, so I can add and subtract them. So if I write down what I have here as two separate things, I have positive 5 plus 4, and I also have negative 5 plus 4, right? Because that 5, I had to have a positive 5 and a negative 5 from right here. So I'm still going to get two solutions. 5 plus 4 is 9, and negative 5 plus 4 is negative 1. So if I graphed this, the parabola of x minus 4 in parentheses squared, and I graphed the horizontal line y equals 25, the x values of their intersection points would be 9 and negative 1. The solutions to this give me the x values of their intersection points. All right, let's try this one. What's inside the parentheses looks a little bit more complicated, but it's still just something squared. So the process doesn't change at all. I have something squared equal to a number. So to get rid of that squared, I'm going to do the square root of both sides. And I'm going to remember to put plus and minus so I get my two solutions. On the left-hand side, squared and square root cancel each other out. I've got 2x plus 3. On the right-hand side, bring down my plus and minus, and I've got square root of 11. So square root of 11 doesn't simplify. There's nothing I could circle if I tried to do a factor tree. So that's as much as I can do over there on the right-hand side for right now. My goal, though, is to still get x by itself. Just like when we were solving equations in middle school, the goal was to get x by itself. The goal hasn't changed, but a little bit of the process maybe has. So let's see what we can do to get x by itself. So I'm going to take minus 3 on both sides. Okay, so this one's a little bit different than the one with the 5 and the 4 because the 5 and the 4 were both integers. We could add them, we could subtract them, but square root of 11 is not an integer. Square root of 7 is an irrational, not 7, 11. Square root of 11 is an irrational number, and so I cannot put those together. The 3 is outside of a square root, the 11 is inside of a square root. I can't combine them as far as making a 14 or making an 8. So what I'm going to do is just write them both negative 3 plus or minus the square root of 11. Okay, and this is actually two things. If you think about it, this is negative 3 plus the square root of 11 and negative 3 minus the square root of 11. So even though it's all written together, this is me getting two solutions like what I wanted to have at the beginning. I divide by 2 on both sides. What I have over here on the right-hand side, this doesn't simplify. 2 doesn't go into 3 or 1. I can't simplify that 11. I can't do a factor tree. So my final answer, negative 3 plus or minus the square root of 11 over 2. So if I put an over 2 here, you can see my two solutions. And if I were to put this one in my calculator, I would get a decimal number. And if I were to put this one in my calculator, I would get a decimal number. And so both of those are real numbers. They're irrational because square root of 11 is not a perfect square, but they're both real so that if I graphed them, I would have an intersection point. This would be the x value of one of them. This would be the x value of another one. This would graph, it just would give me decimal numbers instead of integers. All right, let's try this one. This one also looks a little bit more complicated, but my goal is the same. My goal is to isolate this squared thing. So before I take the square root of both sides, I have to move this. This 5 is not squared, so I have to move it away from the squared thing before I can do anything else. So let's subtract 5 from both sides. So I've got 4 minus 3x squared on the right-hand side, and the left-hand side, negative 29 on the right-hand side. So now look, I have the squared thing by itself. I have isolated it. I am ready to take the square root of both sides, and I will remember to put the plus and the minus right there because I have two solutions. So on the left-hand side, squared and square root are inverses. We're left with 4 minus 3x. On the right-hand side, okay, 29 is prime. Can't do a factor tree on 29. Nothing will come outside. But how about that negative right there? That negative will come outside as an I. This is an imaginary square root of 29. Okay, so I'm not done at this point, right? I don't have x by itself. That's my goal. So I'm going to subtract 4 from both sides. All right, and like before, I square root of 29 and negative 4 are not like terms. So I can't actually put them together. I'll just put the negative 4 first, and we generally do that, and you'll find out in another video why. Still trying to get x by itself. I'm not done. I've got to move that negative 3. Negative 3 times x, opposite is divide. And I'm left with that. And so nothing cancels, nothing simplifies. That is my final answer. And so I'm going to get this. Usually on standardized tests, they won't leave that negative in the denominator. So they'll divide everything by a -1 and change the values. But otherwise, this is the final answer like you would see in the back of the book or on a standardized test. All right, look at this last one. I won't have time to finish it, but I did want to start it with you. I need to get the squared thing by itself. So I'm going to subtract the 7 And then I'm going to divide by 2. And it's important to do it in that order, just like you would a regular equation. Add and subtract first, and then go back and do your division afterwards to isolate the squared thing so that you can take the square.